In organic chemistry, distinguishing between primary, secondary, and tertiary amines is a fundamental task. The Hinsberg test provides a reliable laboratory method to identify these classes based on their reaction with benzonesulfonyl chloride and subsequent solubility in alkaline solutions. The key player here is the Hinsberg reagent, known as benzonesulfonyl chloride. This electrophilic reagent reacts with amines that possess replaceable hydrogen atoms on the nitrogen, leading to different outcomes for each amine class. The process begins with a nucleophilic attack. The nitrogen's lone pair in the amine attacks the sulfur atom in the reagent, displacing a chloride ion. This reaction forms a sulfonamide, but the properties of this product depend on the amine's original structure. Primary amines react to form N-alkylbenzene sulfonamides. Crucially, these products still contain one acidic hydrogen atom attached to the nitrogen. This specific structural feature is what allows us to distinguish them in the next step of the test. Because the sulfonamide from a primary amine has an acidic hydrogen, it reacts with added sodium hydroxide to form a soluble potassium or sodium salt. Visually, the initial precipitate dissolves, resulting in a clear, transparent solution. Secondary amines also react with the Hinsberg reagent, but the resulting N-diacylbenzenesulfonamide has no acidic hydrogens left on the nitrogen atom. This fundamental difference dictates its behavior when a base is introduced to the mixture. Since there is no acidic hydrogen to react with the base, the sulfonamide remains insoluble. Even after adding sodium hydroxide and shaking the tube, the precipitate persists, indicating that the starting material was a secondary amine. Tertiary amines lack any hydrogen atoms directly attached to the nitrogen. Consequently, they cannot form a stable sulfonamide bond with the Hinsberg reagent under standard conditions. This lack of reaction is our primary clue for identification. In the alkaline test environment, the tertiary amine remains insoluble. However, if you add dilute hydrochloric acid, the amine forms a soluble quaternary ammonium salt and dissolves. This solubility in acid confirms the presence of the unreacted tertiary amine. Let's look at methylamine, a primary amine. It reacts to form a sulfonamide that dissolves completely in sodium hydroxide. If your unknown sample clears up after adding base, you are likely dealing with a primary amine like this. Next, consider dimethylamine, a secondary amine. It forms a solid sulfonamide that refuses to dissolve in the alkaline solution. The presence of a persistent precipitate after the addition of base identifies the sample as a secondary amine. Finally, trimethylamine, a tertiary amine, does not react to form a sulfonamide. It stays as an oily layer or precipitate in the base but dissolves once the solution is acidified, completing our diagnostic profile. To summarize, primary amines form products that are soluble in alkali. Secondary amines form products that are insoluble in alkali. Tertiary amines do not react and remain insoluble in alkali but dissolve in acid. When performing the Hinsberg test, always wear proper safety gear and work in a fume hood, as benzonesulfonyl chloride is corrosive. Keep in mind that very long-chain amines might show slower reaction rates due to steric hindrance. Test your knowledge. If an unknown amine reacts to form a precipitate that remains solid even after adding sodium hydroxide, which class of amine are you observing? Think about the acidic hydrogen requirement. The answer is a secondary amine. Because the resulting sulfonamide lacks an acidic hydrogen, it cannot form a salt with sodium hydroxide, leaving it insoluble in the alkaline solution. The Hinsberg test remains a cornerstone of classical qualitative analysis. By observing solubility changes, you can quickly categorize any simple amine. Thank you for watching this chemistry guide. Generated by Vision Solve AI.